Welcome to this lesson on throughput. Throughput is one of the most important concepts in computing and networking. It refers to the amount of data that is successfully transmitted or processed per unit of time. Think of it like a water pipe. Throughput is how much water actually flows through the pipe every second, not just how big the pipe is. In networking and computing, we measure how much data, measured in bits or bytes, successfully travels from one point to another in a given time period. Understanding throughput is essential for evaluating the performance of networks, storage systems, and digital infrastructure. Let's explore the key characteristics that define throughput. First, throughput is always measured in units of data per time. The most common units are bits per second, abbreviated as BPS, megabits per second or Mbps, and gigabits per second or Gbps. Megabits means 1 million bits, and gigabits means 1 billion bits. Second, throughput is time-based, meaning it is always expressed as a rate over a specific time period. You cannot talk about throughput without mentioning a time component. Third, throughput is context-dependent. The actual throughput you experience depends on many factors like network conditions, hardware capabilities, and software efficiency. Finally, throughput serves as a performance metric. It tells us how efficiently a system is operating and what it is capable of delivering. Let's look at some real-world examples of throughput that you might encounter in everyday life. A typical home Wi-Fi connection has a throughput of around 100 megabits per second. A 4G mobile network usually achieves about 50 megabits per second. Enterprise fiber connections used in businesses can reach 10 gigabits per second. Solid-state drive, or SSD read speeds, reach about 3.5 gigabits per second. Satellite internet, used in remote areas, provides around 25 megabits per second. Universal Serial Bus 3.0, or USB 3.0, which you use for transferring files to external drives, offers about 400 megabits per second. These real-world examples show how throughput varies dramatically depending on the technology and use case. Several factors influence the throughput of a system. First is bandwidth, which is the maximum capacity of a communication channel. Bandwidth sets the theoretical upper limit for throughput. Second is signal quality, which includes noise, interference, and signal strength. Poor signal quality reduces actual throughput even if bandwidth is high. Third is network congestion, meaning the traffic load and competing data transfers happening at the same time. When many users are using the network simultaneously, individual throughput decreases. Fourth is hardware capacity, including the processing power and memory available in devices. Outdated or weak hardware limits throughput. Fifth is distance and latency, the physical distance data travels and the delays involved. Longer distances and higher latencies can reduce throughput. Finally, protocol overhead refers to the extra data needed for error checking, headers, and protocol requirements. This overhead reduces the actual useful data throughput. It is important to distinguish throughput from other related networking concepts. Throughput is the actual data successfully transmitted per unit time. It is what really gets through the system. Bandwidth, on the other hand, is the maximum capacity of a channel. It is the theoretical upper limit, not what actually happens. Latency is the time delay for data to travel from source to destination. While throughput measures speed of data volume, latency measures speed of individual data packets. These are different measurements. Goodput is another related term meaning useful data delivered, excluding protocol overhead. So goodput is throughput minus the transmission control data. Understanding these distinctions helps you properly evaluate network and system performance. Throughput is critical across many modern applications. Video streaming requires consistent throughput of 5 to 25 megabits per second to deliver quality content without buffering. Cloud services depend on throughput for the speed of uploading and downloading files, typically requiring 10 to 100 megabits per second. Online gaming needs 3 to 25 megabits per second of throughput to keep gameplay smooth. Enterprise systems handle database queries and large file transfers, requiring 1 to 10 gigabits per second. Mobile networks must handle simultaneous users and heavy usage, managing 50 to 500 megabits per second. Data centers maintain high-speed connections between servers, requiring 10 to 400 gigabits per second. Understanding and optimizing throughput directly impacts user experience and system efficiency across all these applications. There are several strategies for optimizing throughput in networks and systems. Load balancing distributes traffic across multiple paths and servers to maximize capacity utilization and prevent bottlenecks. Quality of service, often called QoS, prioritizes critical traffic and manages network resources efficiently so important data gets priority. Data compression reduces the size of data before transmission, which increases effective throughput by sending more useful information in the same time. Infrastructure upgrade means investing in newer hardware and faster network technologies to increase raw capacity. Performance monitoring involves continuously measuring and analyzing throughput to identify where problems occur. Protocol optimization uses efficient communication protocols and minimizes overhead in data transmission. By implementing these strategies, organizations can significantly improve their data transfer rates and system performance. Let's review the key takeaways from this lesson. First, throughput measures actual data transmission success. It is not just about capacity, but about what actually gets delivered. Second, multiple factors influence throughput in real-world scenarios. Network conditions, hardware, distance, and many other variables all play a role. Third, understanding throughput is critical for system performance planning. Whether you are designing a network or evaluating a service, throughput matters. Fourth, optimization strategies can significantly improve data transfer rates. There are practical ways to enhance throughput through better design and management. Finally, remember that throughput is fundamental to evaluating network and system performance across all digital infrastructure. Whether it is the internet you use at home, mobile networks, cloud services, or enterprise systems, throughput is the metric that matters for performance.
If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.